All right, and so being able to use the chain rule and see, ultimately, you can see that lately in most of my lectures, when it comes to chain rule, I got really excited to show my students about how to use a chain rule. But here for logarithms, I have to point out a couple things right here. Now, so using chain rule is good, and being able to apply chain rule into your logarithm expression to find the derivative is perfectly good. But sometimes if we just directly apply the chain rule immediately, the first thing is not always a good idea. So if we are able to bring in some algebraic property of the logarithm function, because logarithm, if you don't remember these properties of the logarithm functions, then I highly recommend go back to your the content of your algebra course or your pre-calculus course to review a little bit on the logarithms. But if we can manipulate the algebraic properties of your logarithm function before we even let the chain rule kick in, or before we can even find the derivative, that would be even better, making our work a lot more effective. Okay, and so I am going to bring up example 3 here, and you will understand exactly what I mean by that. So now let's look at example 3 right here. Okay, and just like that, we are going to find the derivative, either writing that as f prime of x, or our derivative can be written as dy dx. Okay, and so here's our function. Here's the first one in our expression. Now, I do remember from the earlier example we had a problem like this, and it's good to do one same problem again. Y equals natural log of x squared plus 5x plus 6. So I remember clearly we had this as one of our example problem in example 3. But this time I am going to give it a different look, a different solution. Okay, and of course we're still going to end up into the exact same final answer. Okay, so if I remember correctly, then I put this in example 2. And the way how we solved example 2 was pretty much we directly, first thing in line, we recognize the inside and recognize the outside and then apply the chain rule immediately. That's all good. But now in this particular example 3, here's my plan. I am not going to rush immediately into using the chain rule yet. This is what I'm going to do. Now, if we can, okay, see right here, this expression inside of your this expression inside of your logarithm, this is just something we observe. So being a math student, one good factor to become a successful math student, have a lot of observations, okay, and keep pushing your observations as detailed as possible. And so the observation here tells me that, hey, we can actually factor this polynomial inside of our logarithms right here. So I'm not going to be too worried about the tracking down the inside function or the outside function or anything like that yet. But just right now, x squared, just quick little scratch work. How about on my other board right here? All right, so as scratch work on my other board, I can see that x squared plus 5x plus 6 can be factored as x plus 2 times x plus 3. Okay, and so, I mean, it might sound a little silly, but if any viewer is feeling shocked about how I got this, please, I highly recommend, if viewers feeling shocked about how I got this, you gotta watch your, you gotta review your algebra content before we can move on further in calculus. Okay. But and so algebra is a massive part of your calculus learning. Okay, so once again, x squared plus 5x plus 6 factor into an x plus 2 and x plus 3. This is a product of two factors right here. So now, how is that useful in our problem here? And I'm not talking about taking derivative or anything like that yet. I'm just manipulating or playing around with the algebra of our expression here, of our function. So now, meaning I can rewrite my natural log or my logarithm as x plus 2. Logarithm of, and the inside becomes a product of x plus 2 and x plus 3. Okay. So that's a different way of how I'm looking at my expression right here, at my function. But now, if you recall from your pre-calculus course, the days that you were learning about those properties of logarithms. So back then, back in those days, of course, I don't blame any algebra teacher that they couldn't point out all the applications, because at that point when you were learning the algebra, you were building up your foundation, and this is where we apply it. Okay, so my advice for anyone, in case anyone still didn't like algebra too much, algebra is the foundation, and now this is where we apply. So just be patient with the algebra. You will see a lot of usefulness with the algebra here. Logarithm, any logarithm, doesn't have to be just base e or whatever. This is natural log, this is base e, but it works the same with other logs, other bases. Logarithm of a product is the same as, and I'm still looking, I'm not doing any derivative yet, I'm just manipulating the properties of logarithm. So logarithm of a product is the same as the logarithm of the first factor in the product plus the logarithm of the next product, the next factor in our product. So back in the days you were learning algebra, this was a property where you turn the logarithm of a product into a sum of two logs right there. Okay, see, the sum of two separate logs, same base. All right, so that's just a manipulation of the algebraic understanding of our logarithm function. And now here's how useful it can be. So now you turn your problem into something one term, one function, but now it's two separate terms. Natural log of x plus 2 is one function, one term. There's a little bit of inside and outside, so chain rule can apply it here. There's a little bit of inside and outside in this term right here. But now hopefully at this point anyone anyone following with this video lesson of mine is hopefully fluent enough with chain rule, so I can start speeding up the chain rule process in each of these. But my main aim is to point out how we can manipulate the algebra behind the scenes before we can apply the chain rule, before we can directly take the derivative. So now here comes our derivative steps. So dy dx, okay. The sum rule says we take the derivative term by term, so I'll take the derivative here and I'll take the derivative there. Taking the derivative on the first term, we have a little bit of inside here. So I have a little bit of inside. See the part I underline with red ink like that, that's where I recommend for my viewers to regard to that as inside. And then here's another inside right here. But that's for, how about, we'll get there when I get there. We'll get there, I'll highlight it when we get there. So for now, we just need to, our main aim is find the derivative of the first term. Okay, so the inside has just now been underlined right here. So derivative, taking the derivative of something like that, chain rule says take the derivative of the outside, so it becomes a 1 over x plus 2. Okay, 1 over x plus 2. And then, and still, I'm only right now focusing on my first term. So chain rule says further that we need to multiply with the derivative of the inside. So x plus 2 is the inside, take the prime of that. Okay, so all that here takes care of the derivative of my first term, natural log of x plus 2. Okay, and then I'm going to hold on to that. I'm going to save that for the next step. So now we're moving on to the derivative of the next term right here. So now I can highlight again. I can underline this is the inside of this second term, the inside of this next term right here. So again, chain rule is about to apply when we attempting the derivative of this. So now the derivative says, the chain rule says that we take the derivative of the outside function, which is now 1 over x plus 3. See, if this is all a u right here, then the derivative of natural log is a 1 over u, but u is, in this case, x plus 3. And now multiply with the derivative of the inside for this particular term, so x plus 3, taking the derivative. Okay? And so now, in my next step, so my fraction in the, so now so one more time, let's swing back to the other board. This term now, the next thing we need to do for that term is take that derivative, but that simply becomes a 1. All right. So now we're looking at, this is just simply now 1 over x plus 2. That's it. I don't have to write times 1. And now plus, let's find out what's the the final derivative for this next term right here. So we already had half of that done. So derivative of x plus 3 becomes a 1 again. So now that means my next term in the next step becomes 1 over x plus 3. And so now we're done. Officially speaking, we're done. Some instructor, including me, some instructors are okay with this way of how you write your final derivative. And then again, if you worry, because I purposely brought up this problem so that you can see two solutions of the same exact problem. So if you look back and review the video and look back at the solution I had in the earlier example of the same problem here, then the answer didn't look like this. It's another algebra matter again. It's just a matter of algebra again. So if we make common denominator, then this is going to be all that x plus 2 times x plus 3 as our common denominator. And then that's multiplied for 1, the x plus 2 multiplied for the other one. So now we're looking at x plus 3 plus x plus 2. Okay. And so now our final expression here, foiling out this x plus 2 times x plus 3 is back to x squared plus 5x plus 6. And now taking away the parentheses here is giving me 2x plus 5. And this is exactly the form that we have seen as the final answer for our earlier problem. I mean the same problem, but when we solved that in our earlier example. Yeah. Okay, so I'm among those instructors who are okay with this form, but there could be other instructors out there who ask their students to bring it all into one form. And it might be me sometimes that I also want to look for, it all depends on the teaching quarter, the academic term, where, you know, if I doubt the comfortability of my on the algebra level of my student, then I have to constantly ask them to do the algebra work on top of the calculus work. Okay, and that's how we are done with part A of our example 1. Let's now look at another example. And now I'm going to allow problems to get bigger. Okay, so now there would be time where your logarithm looks like this. We can have a natural log of x plus 3 over x plus 5 raised to the 4th power. Okay, and all that there. Okay, so we got logarithm, natural log, and then inside of the natural log we have x plus 3 over x plus 5 all raised to the 4th power. Okay, so if we want to directly use the chain rule, then yes, good thing I can bring up. This is the inside right here, a good considerable inside because it's inside of your natural log. But even though I recommend that being the inside, I wouldn't go that way because it's going to take a lot of steps. Especially the inside itself is still quite crazy looking because, you know, even if when you later on find the derivative of this inside, you're going to chain yourself into another chain of chain rule. Okay, so how about let's hold on to the idea of using direct chain rule here. Let's apply the algebraic property of your logarithm function. So this is what I can do. And again, this is only the algebraic workaround. Okay, it's just we're working around with the expression before we actually find the derivative. So notice that this is a logarithm of a power. That's the first thing, because this power 4 here is outside of that x plus 3 over x plus 5. So in other words, you know, we got the 4th power of the entire quotient here. And so in that way, recall for yourself, and this property is the same for any other logarithm. You got an expression being raised to a power, okay? And taking logarithm of a power means, and this is not the power rule for taking derivative. Please do not confuse these two. And of course, eventually you're going to see they are the same name but being used in too many places. So make sure you understand clearly what you're doing. This is logarithm of a power. Okay, but this is how we do. This is the algebra of logarithm of a power over here. We can bring that power in front. Okay, it's so dangerously looking like the power rule that we've just learned in this calculus quarter, but it's not. Okay, multiply with logarithm of just the expression without the power. Okay, it's not like I'm subtracting the power by 1. Okay, it seems silly now. Anyone viewing this video might be cracking down and laugh, but at some point you will make that similar mistake. So watch out for these things carefully. You're not going to subtract the power here by 1. Once you brought that power out front as a coefficient, this remains no power, or actually I shouldn't say no power. It's a little bit illegal, but power 1 here. Okay, and because power 1 we don't write the power. That's why. So now, how is that useful for this problem? Now let me erase that to make myself some more space. But that power 4 now becomes the coefficient 4 before my log. So now I have 4 times natural log. Okay, and now surprisingly the expression inside of the logarithm is only now x plus 3 over x plus 5. Okay, and now if anyone who loves using the chain rule so much is going to start, hey, feeling so ready to find the derivative by letting this be in the inside. But I would say, hold on. I know you're excited to apply the chain rule, but you can still do some more treatments to this, because your inside right now is still a little bit complicated, and I wouldn't go that way either, even though you could. Okay. So another property of logarithm, recall for yourself, logarithm of a quotient algebraically can be rewritten as logarithm of the numerator. Subtract logarithm of the denominator. So we can turn logarithm of a quotient into the difference of two logs. Be cautious. Make sure the order of the subtraction comes out comes out like how we have the quotient. A is on top, then natural log of A comes first. Okay, B is in the bottom of our original denominator. In the bottom of our original quotient, then natural log of B comes after the subtraction sign. Okay, so how is this useful for our current problem? Right here, this is A, numerator. All that x plus 5 is B, the denominator. And we have a total coefficient 4. So in the next step, I would write y equals 4. And I'm going to open a pair of brackets right here. But now I'm looking at logarithm of x plus 3, natural log. That's what I meant. Okay, minus natural log of x plus 5. Okay, and again, I have to emphasize, we're not doing derivative yet. Okay, we are only turning the expression around and around. So that, but at least things like this is now a lot simpler to handle, because and then I can go ahead and distribute my coefficient for each term here. So that means in my next step, y equals 4 times natural log of x plus 3. So this can now be done similar to part A of our example, minus 4 times natural log of x plus 5. This is not the derivative, ladies and gentlemen who are viewing my video. It's only some expression that's making it easy to take derivative term by term. Okay, and so now we are ready to find the actual derivative, and then it looks like I must use my other board to find this derivative here. All right, so before I'm completely moving out to the other board, so let me explain. So now whoever loves using the chain rule, here's your chance. We can now first take the derivative term by term. So the first term to come, for the first term, it has this 4 coefficient multiplied with the logarithm, and then the inside of the logarithm is a lot simpler than any of these things. If we were choosing this, good luck with that route. If we were choosing this as your inside, well, it's not as bad as this, but it's still a good luck for that, because we might make a mistake all over. But now the chain rule here, using the chain rule for that term, taking that as the inside is a lot easier. Okay, so now I'm going to find the derivative of that first term. So in my next board, this is what I'm doing. So dy dx now, and you have seen the similar action from part A of our example. So I'm going to speed it up a little bit. So it's coefficient 4 stays the same. Now it's 1 over x plus 3. That's the derivative of the outside. And I'm going to multiply with the derivative of the inside, which gives me simply 1. The derivative of that part I underline in red right there. The derivative of this thing. It's a chain. It's an inside. So we got to use a chain rule, but it's a lot simpler than compare with if we were using the derivative there. Okay? And now let's move on to the next term. So here we need to find the derivative for that term for natural log of x plus 5. I am again recommending to use that as my inside right here. And so into my other board, that will become 4 times 1 over x plus 5. This is for the derivative of the outside function. And the chain rule says we multiply with 1 as it's for the derivative of the inside I underlined in red ink earlier. And so now our final expression, we are ready for it. Our final dy dx. And this is already our derivative, but maybe it's a little better it would be better if we write it all as 4 over x plus 3 minus 4 over x plus 5. Okay, that's one way to write your final derivative. All right, so there are instructors who are okay with this, asking their students to leave the answers like this, and sometimes I'm among them, sometimes I'm not. So in case you are asked to combine all this into one fraction, then we take a little further algebra. But notice this is already the derivative. So the rest is just how we use the algebra to turn your derivative into different expression. And so we can make a common denominator. So here I'm looking at 4 times x plus 5 for the first term minus 4 times x plus 3. Okay, for the other term, and putting that all in one common denominator, x plus 3 times x plus 5. Okay, and now it takes a little bit. It just takes a little bit of time to take the parentheses out there. We're looking at 4x plus 20 minus 4x. Watch out for sign change. Minus 12. Okay. Minus 12, and then my denominator here turns into, after FOILing out, we're looking at x squared plus 8x plus 15. Okay, and the 4 x's in my numerator are opposite terms, they cancel out, and then 20 minus 12 gives me positive 8 over x. I need the fraction bar to be a little longer. Okay, so x squared plus 8x plus 15. Okay, and that's how it's done. All right, so that's the derivative of our function that started from the beginning. It was way complicated looking, but now manipulating the algebra of your logarithm. Okay, so at this point, you can, and trust me, as we go along with the quarter, you will realize how important the algebra that you have learned in your past. So keep going back and keep outside of learning our lecture here, grab an algebra textbook and feel free to review for yourself on all that algebra technique. And no matter how far you're going in calculus, or no matter how far you go in math, you will always need the algebra as your foundation. It's like if you want to build a big building, you got to have a strong foundation. Otherwise, your building is going to collapse. Okay. So that's how we find the derivative of our problem in part B. So let's look at another problem, and I purposely brought up this example 3 so that you can see, and as you learn through these examples, you recall for yourself a little bit more about you review for yourself a little bit more about the algebra properties of logarithms. Okay, so let's look at. So now let's say we can have something like this. Question C. Okay, y equals, how about natural log of, and now I'm looking at, let's say, 8th root. Okay, 8th root of x squared plus 7x plus 12 being inside the 8th root. Okay. And so this problem can be treated very similar to the earlier problem, in a sense that, see, recall that logarithm of a power. Okay, I brought up this property earlier. Logarithm of a power is the same as bringing that power in front as a coefficient. And then the expression inside the log now no longer need to have that power. It's just now power 1. Okay, always. So it's not like a n minus 1 here. But now, how is that useful here? Because any root, 8th root of any expression is the same as algebraically regarded or understood as 1 over 8 power. So there's a power form there. All right, so that means here's how useful we can apply our understanding into this problem. Y equals, now I can bring the 1/8 in front. You know, let's not rush anyone viewing my video. So I'm going to take time to write one more step, even though in practice you probably don't need to do this. So x squared plus 7x plus 12 okay, raised to the 1/8 power. Now I successfully display the power nature, because what we have here is that the entire expression x squared plus 7x plus 12 that is trapped inside the 8th root right here is now being the expression but raised to the 1/8 power. Okay, and now with that property, I mean the property on logarithm of a power, now I can go ahead and bring the 1/8 in front and rewrite my expression as x squared plus 7x plus 12. Okay, and so see, definitely we don't want to take all that expression here as the inside. It is the inside, but we don't want to take an inside like that, because eventually when you take the derivative of the inside, it's going to lead you into another chain of chain rules. And even if we're looking at this inside here, I mean it's already pretty good so far, but I still recommend go further if we could. So put in some more observations. What do we observe here? X squared plus 7x plus 12 can actually be factor. Okay, so in case that the quadratic here, you know, is not factorable, then go ahead and take all that as an inside function and start applying your chain rule from here, which is just fine. But since I can break it down even further, then let's do it. So that means I'm looking at 1/8 times natural log of x plus 3 times x plus 4. You see, if we can keep breaking it down to smaller little chunks, why not? Because each little chunk is a lot easier to find the derivative, including, you know, the chain rule steps being chained in there. Okay, and so now once we have recognized it this way, it's a product of two factors. Now we can write our final function as y equals 1/8 times natural log of x plus 3, all right, plus a separate 1/8 allow me to skip that step of, you know, keeping the 1/8 here as a common factor, but it is common factor, but I already distributed it. Okay, natural log of x plus 4. Okay, so now taking the derivative term by term here is a lot easier. It's a much easier work for here. So now at this problem, since we have seen the kind of action here quite a few times, so allow me to start speeding up the process a little bit. So I'm going to now take my derivative of the first term here. There's the outside is the natural log, and the inside is here. The inside is here. Okay, and so now in my next board, the derivative becomes of that first term. Now we're looking at dy dx equals, we have the 1/8 there, 1 over x plus 3 times 1. All right, and now I am going to add. Now let's one more time look back at the expression we had in the beginning. And this is, remember, this is your beginning function, your original function. And then I didn't take the derivative until when I get to that other board right there. But so now in this next term, because derivative allows us to take derivative term by term, derivative rules, This is the inside of our next term here. The 1/8 plus, 1/8 times the natural log of x plus 4. This is one entire term, and so the inside is being underlined in red right there. Okay, and so now we're looking at 1/8 times the derivative of that. Outside derivative is 1 over x plus 4 times the inside derivative, 1. Okay, and so now that is just now in one fraction for the first term. 1 over 8 in parentheses x plus 3 plus, and then 1 over 8 in parentheses x plus 4, and that is how we've got our derivative for that function. Or we can take our time a little bit and doing this common denominator. So I have x plus 4 to be added with x plus 3, okay, and all over. And so now 8 is already a common factor, so we only need to multiply these two. So now we're looking at 8 times x plus 3 times x plus 4. Okay, and so now taking the parentheses away, we're looking at 2x plus 7, and now 8 times, and I'm leaving all that here, x squared plus 7x plus 12 in the denominator. We're done again in a different way to express our final derivative. Okay. All right, so how about one more problem in example 3, and that should be it for our example 3. And you have seen a good amount of problems where it represents the kind of generality here in example 3 here. So problem D, how about y equals, and we're looking at the natural log of, and I could have done that with other log as well, but you know, the natural log is simply it less work for us. So a lot of time, and I'm not the only instructor doing this. Many other instructors, when it comes to taking derivative of logs, most of the time they stay with the logarithm, natural log, okay, log base e. But now I'm looking at logarithm, natural log of x to the 8th, okay, x to the 8th in products with x plus 5 to the 5th power, okay, in products with x minus 4 to the 7th power, okay. Oh boy, good thing we were not asked to factor something like this because it's already in factor form, okay. But you know, if it was really all in factor, all foiled out and asking us to factor it in something like this, then you know we're gonna have to be a lot more patient in that. But I wouldn't do that to my students, and I hope no instructor is doing this to any students there. But so back to this problem itself, the good news is that it's already all in factor form, making it easy for us to recognize and start blending in those algebraic properties of our function. So there's a product here, okay? So that means I can consequently, and again, right now I'm only manipulating around with the algebra properties of logarithm, but I'm not doing anything with derivative yet. So being product, I can now go ahead and break it down as 3 separate logs. Logarithm of 8, natural log of 8 plus natural log of the x plus 5 to the 5th power, okay, and the natural log of the x minus 4 to the 7th power, okay. So that's breaking it down right there, and now each of my logarithm here, their inside is being some power. So there's a power 8, x to the 8. This is x plus 5 in quantity to the 5th. This is x minus 4 in quantity to the 7th. So now we can apply the rule for a power inside of log. And so y equals, now this is 8 times natural log of x plus, this is now 5 times natural log of x plus 5. So you see now each of the expression inside the log is a lot simpler. plus. Now I can bring down that power in front, 7 times natural log of x minus 4. Okay, so now I have to make clear again, this is not the derivative, this is only some, I would so-called final expression of our current function. But the good thing now, even though we got 3 different terms, but the good thing now is that each little term is a lot simpler to find, okay? And if you want to apply the chain rule for each one of these terms, so do it. But if you want to apply the chain rule right here, where you are planning to take the entire thing here as the inside, well, you don't even want to void this out and take all that as an inside as well, okay? And so my point now is that taking all that here as an inside from right from the beginning and apply the chain rule is way too much work for us. So taking a couple of steps, break it down something like this, it's a lot faster, okay? And so now I have enough space to kick in my actual derivative work here. So dy dx here now going to be first term. That 8 is only a coefficient. So now we're looking at 8 times 1 over x. Surprisingly, we're done for the first term. Okay. Next term, notice how the 5 is a coefficient. So keep it there. 5 times a natural log. Wrong again. This is so derivative of natural log. But chain rule, I can recommend that I recommend taking that as the inside of our log term right there. So now the chain rule says take the derivative of the outside. Now we're producing 1 over x plus 5. Okay, and then multiply what chain rule says, multiply with the derivative of what's being underlined here, 1. Okay, and now next term, coefficient stays the same, 7, and now and I keep mistakenly writing natural log for some reason. But now here again, I recommend this could be used as a good inside. So derivative, chain rule says take derivative of the outside, so 1 over x minus 4, and then multiply with the derivative of the inside, which is simply 1. Okay, and so now in my other board, I'm simply just gonna write the final answer after cleaning up the terms a little bit, or re-expressing the terms a little bit. All right, so my final expression. And for this problem, I'm not going to worry about putting that into a one fractions simplified version anymore. I can leave that for you. So here I'm just going to have 8 over x plus 5 over x plus 5, okay, plus 7 over x minus 1. And I'm not going to worry about getting that into the simplified expression of this. And you can still do that, but my main aim for this problem was for you to understand that how we already applied the algebra before we took the derivative. And the algebra was, to me, when class was still a face-to-face class, I referred to any algebra steps before taking the derivative as an algebra treatment. We treat the problem to make it easier for us to take the derivative. Okay? And so that's how I end with example 3 right here in our particular lecture here.